In this video, I want to talk about simplifying rational functions and why it's so important. Now, a rational function, again, any function that can be written as a quotient of two other functions. So you see this first example, I have a line divided by a parabola. Now, in terms of simplifying, what we're really looking for is, do these two functions have something in common? Now, if you remember from our earlier work on factoring, we could say, well, the bottom, x squared plus 6x plus 8, could be rewritten as a product of two factors. The two numbers that would multiply to 8, let me just make my notes like I typically do, and then we pick the pair that also adds up to 6. So it's going to be x plus 2 and x plus 4. Now, we know that, I'm going to just cross this out since now the function's divided by x plus 2 and x plus 4. We know that rational functions, we need to be concerned with the denominator being 0. We can't divide by 0. So right away we should be thinking, okay, negative 2 is going to cause us an issue, negative 2 plus 2. And negative 4 is going to cause us an issue because negative 4 plus 4 is 0. We shouldn't have a 0 in the denominator. But you will notice that both of these, the numerator and denominator, have an x plus 4. And we can think about those as dividing out. Something divided by itself is 1. So x divided by 4 or x plus 4 divided by x plus 4 is just 1. And this simplifies to be 1 over x plus 2. Let me show you a graph, and that'll, I hope, indicate why this process is important. Here's the graph of the function we just worked with, x plus 4 over x squared plus 6x plus 8. And we've talked earlier about asymptotes, these spikes in the graph that occur when I'm dividing by 0. You'll notice there is only one. There is not one at negative 4. There is only the one at negative 2. Only the simplified version had the asymptote indicated. So that's why it's so important. Now, what happened at negative 4? What happened at the one that we divided out? That's actually a hole in the graph, and we're going to come back to that later. It's still a problem. It's still a domain issue that we shouldn't be plugging negative 4 into our function. But the only spot that we actually have the asymptote is at the negative 2 indicated by our factored version. Let's do another example. Now this next example, the only thing I can kind of immediately think that I might want to factor out is a 3 in the numerator. So if I did that, if I divided a 3 out, it would leave me with x plus 3. Let me kind of cross this out. You'll notice we have an x plus 3 in common, and dividing those out, that divides to 1, and all that's left is a 3. So even though I have this rational function, it ends up just being the number 3, which is a horizontal line. Let's take a look. Take a look. Even though it looked like a very complicated function, just ends up being a horizontal line located at 3. All right, the next example looks like I can actually factor both the top and the bottom. So let's do that. The two numbers that would add up to 4 and multiply to 3 would be 1 and 3. So this could be x plus 3, x plus 1. And this bottom thing, this is the difference of two perfect squares, so we need x plus 3 and x minus 3, and that way it adds up to 0 and we lose that middle term. Well, you look for that common factor. They both have an x plus 3. I would divide that out, and we're left with x plus 1 over x minus 3. So again, 3 would be our, I'm going to make a note, vertical asymptote. Finally, the hardest thing to factor, I think, is when we have x's and everything and numbers and everything. So let's look at an example of that. So this example, you can see on this first, on the numerator, that every term has an x, but every term also is divisible by 3. So if I were to divide out a 3x out of everything, I would get 3x and then multiplied by x plus 3. I would always just double check this, 3x times x is 3x squared, 3x times 3 is 9x. And kind of going the opposite way, as you're doing your factoring, just think what they have in common and divide that out. That's what factoring is. It's undoing that multiplication. So you say, well, I can divide a 3 out. So 3 divided by 3 is 1. 9 divided by 3 is 3. And then, x squared divided by x is x. And x divided by x is just 1. Now on the bottom, they're both divisible by 6, so I could pull that out. They also both have an x squared. You can only pull out what they both have. So let's pull out a 6 and an x squared, and that would leave us with 2x plus just 1. Again, I just stop. 6x squared times 2x is 12x cubed. 6x squared times 1 is 6x squared. Now, let's look for what we can, what they have in common. I would look at this. I'd say they both have an x, right? X and x squared, but we could take out or divide out an x. I'm going to do this. Rather, let's do that, and then I would still have an additional x on the bottom because I have two of them. I've got x squared. But then also, I have this, 3 and 6, which I could reduce to 1/2. So on the top, I would just be left with an x plus 3. And on the bottom, I would be left with a 2x and then 2x plus 1, like that. And let me just recap that. The 3 over 6 reduces to 1 divided by 2. I don't really need to write a 1. The x divided by x squared would reduce to 1 over x. Again, I don't really need to write the 1. So that just has an x plus 3, and then I still have that 2x plus 1. So when you're simplifying rational functions, I would start by looking to factor them. And then once you've done that, look for anything they have in common that could be reduced. And the point of this will be looking for vertical asymptotes versus just discontinuous points or holes in the graph. If this video helped, please like and subscribe for more math help.